All right, everybody. This is a good angle, I believe, for the board. And I am going to get started in a minute for Unit 6 review. Okay, so in Unit 6, there were very many learning objectives. But if you look at the big ideas, there were a couple big ideas, not as in big idea of College Board, but important concepts there were Lewis structures, VSEPR, hybridizations, and the second part of it was bonding. So I'm going to address each one by one. So the first set of learning objectives that you had were around Lewis structures. I'm going to zoom it in a little bit. Lewis structure, who's logged in? Somebody's there. Can you see this? Whoever is online, watching from online, can you tell me if you can see the board all right at the Zoom? Or do I need to move it any closer? Maybe I can move a bit more. Okay, now this is definitely better. Okay, so Lewis structures, VSEPR, and hybridization. And in there somewhere I'll talk about sigma and pi bonds and so on. So first thing is Lewis structures. And for drawing Lewis structures, you draw these 2D diagrams or drawings to show how in covalently bonded molecules, electrons are shared or just stay on the central atom. And there are 5 steps for doing it. Even though primarily Lewis structures are for covalently bonded molecules, you can use Lewis structures for ionic compounds. For example, for NaCl, its Lewis structure will look like this, where there is an empty valence shell for sodium ion because all its electrons have been lost, and has its completed valence shell. For a covalent molecule, Br, was it with a plus charge? I don't remember. Let's try BRF5, right? If we have to draw this, then we go to step 1, which is how many valence electrons are there in the entire system. Bromine has 7. Each of the fluorines have 7. So 35, 42 electrons. How many does it need to be happy? 8 times 8, because none of these are exceptions. How much? 48 electrons. And how many bonds? 3. And you know at this point that this is an exception because minimum to attach each Br to the F surrounded, you need 5 bonds. And if you're coming with 3, you know it's an exception. In that case, you cannot follow the step. You go to plan B. And plan B is to attach each of the atoms around it with a single bond. You do not put multiple bonds. Single bonds and complete each side atom's octet. And that gets us to 40, but started with 42 electrons, right? 8 times 4, 5, 40 electrons. So you put the extra on the central atom as a lone pair. If there were 44 electrons, you'll put 2 lone pairs on the central atom. So here, this was plan B. Another thing to remember in Lewis structure is sometimes you can have resonance. For example, if you are drawing carbonate ion, CO3, 2-, remember you'll come up with 4 bonds. And when you come up with 4 bonds, but there are only 3 things around it, so you can put a double bond, but that double bond is a traveling double bond, meaning sometimes it is here, sometimes there. And in that case, what you do is use formal charge to figure out which is the best structure. And when you use formal charge, what you realize is that all of these are equivalent structures supported by formal charge, and such a phenomenon is called resonance. If an ion or a molecule shows a resonance, you must draw all resonance structures. Okay, next thing that you need to know here are exceptions. So exceptions to Lewis structures. Lewis structures is based on the concept of completing the octet. Now, sometimes the molecules do not believe in completing the octet. So there are exceptions on lesser than 8 electrons, like hydrogen, helium, beryllium, and boron. You got to remember these 4 atoms. Hydrogen and helium are happy with 2 electrons, beryllium with 4, and boron with 6. So when you do step 1, how many does it need to be happy? If you had beryllium, you will only put 4 and not 6. This you must memorize. For the high-end exception where there's expanded octet, you will know that because your total number of bonds will come out lesser than what you minimum need. In that case, you go to plan B as we did for BRF5. Other thing you got to remember here is bond order. Bond order is number of bonds. I'll come back here. That is not real visible. Bond order means number of bonds between any 2 elements. Like if you have ammonia structure like that, and you're looking for bond order of NH bond, it is 1, right? But in case of the resonance structure, bond order is all of these added together. Like there are 4 bonds in 3 structures, so bond order is 1.33. So bond order can be fractions as well as whole numbers. And that pretty much is about Lewis structures. The add-on to Lewis structures is VSEPR structures or VSEPR theory. VSEPR theory or valence shell electron pair repulsion theory says that if you have a Lewis structure, using the Lewis structure, this theory can tell you how the molecule will look in 3-dimensional space. So, for example, ammonia, if you draw its Lewis structure, then VSEPR theory will tell you that this molecule will be like a trigonal pyramidal. How this theory does that is by assumption that electron domains tend to be as far from each other as possible to minimize repulsion. So when around the central atom, you have 2 side atoms, the farthest they can be from each other is 180 degrees. And here, the molecular and electron domain geometries are both linear. I'm going to erase the other side of the board and put it over there so you can all see it clearly. So VSEPR, valence shell electron pair repulsion theory. There are few things you must know about this theory. This theory says that a lone pair repulsion is greater than a lone pair and a bond pair than a bond and a bond pair. That's because lone pairs are present on the electron cloud of the atom. They're closer together than a bond pair, which have internuclear access to separate out. Okay, so that is one thing you need to remember. Other thing you need to remember is single, double, or triple bonds are treated same in this theory. they are treated as one electron domain, single electron domain. So whether it's single, double, or triple bond, it's all the same. So now let's look through VSEPR theory and let's draw structures. So electron domain geometry, molecular geometry, bond angle. Okay, so if we have a molecule like this, you have the central atom and you have two side atoms. The farthest they can be from each other is 180 degrees. So the bond angle is 180 degrees, and electron domain is linear and molecular is linear as well. The examples here could be CO2 molecule, C double bond O, right? That is an example of it. The second one type is when you have a central atom and you have three side atoms all in the same plane. They are in the plane of this whiteboard, and the bond angle in that case is 120 degrees. And because there are no lone pairs here yet, the geometry is trigonal planar and trigonal planar. And guys, by the way, if we are talking about polarity of the molecules, based on 3D shape, you can also predict if a molecule will be polar. And that's got a lot of implications because many properties such as solubility or melting point depend upon polarity. So here, even if these bonds were polar, because the molecule is linear, they will cancel each other out and the net dipole will be zero. Even though it's got polar bonds, the molecule will be non-polar. The same thing here, that if I am drawing, I shouldn't blanket draw it because it depends on if the central atom, typically central atom is more electropositive. But if I were to draw carbonate ion, then that is this geometry we are talking about. And here, because they are all in the same plane, there's no lone pair on the central atom. The individual dipoles cancel each other out, and net polarity of this molecule is zero. This is trigonal planar. Now here, there can be that this is AB3 molecule. You can also have AB2E molecule. AB2E is one of these become a lone pair. In that case, what happens is you have central atom and you have two side atoms, but the third one has become a lone pair on the central atom. It is not through a bond. So when we talk about electron domain geometry, in that case, we do treat this lone pair with a bond. If the lone pair were to be present with a bond around the central atom, what would that geometry look like? So its electron domain geometry, or geometry of its electron domain, is still trigonal planar, but its molecular geometry starts looking like this because the molecule is only this, right? And the lone pair really is sitting in the electron cloud here. And because this lone pair repels the bond pair more, this angle becomes less than 120 in this case. And this shape is called as bent. You have to memorize the bond angles and the shapes. So far, so good? Yes.
Does the Quizlet have everything we have to memorize?
I haven't checked it, but would one of you be kind enough? Basically, you need to know AB2, AB3, AB2E. Let me write these here. So what you need to know is AB2, AB3, AB2E. They are one thing, right, with a lone pair. AB4, AB3E, AB2E2, AB5, AB4E, AB3E2, then AB6, AB5E, and AB4E2. You need to know all of these. Okay, that's pretty much all of them. Yes.
Do you know if the chart in our pink packet has all of them?
It has all of them. The only thing that is not there in your pink chart are the two specific bond angles. Typically, when you have lone pairs, it's okay to say less than the electron domain geometry bond angle, right? But in case of AB3E and AB2E2, you need to memorize specific bond angles. Saying less than 109.5 is not good enough. You should say 107 here and 105 here. And guys, this 3D geometry impacts the polarity of the molecule. For example, this molecule would be nonpolar, but if you replace it with a lone pair of electrons, it becomes polar. So at this point, we have a decision to make. I would ask you, do you want me to go through the entire table? I can do that, but that will cut away time from the other things. If you have a need for me to go over one more or many more, let me know. Hybridization. Okay, all right. We're going to hybridization. So hybridization happens when the atoms come together to form a molecule, and hybridization impacts the central atom in a molecule. I'm going to erase this here, but I'm going to leave that there. So in hybridization, first of all, you need to know it happens on central atom, not on the side atoms. So in carbonate ion, what you need to do before you can predict hybridization is you need to draw its Lewis structures, right, with the bond angles. And then you recognize how many single, double, or triple bonds are here. You recognize how many electron domain irrespective of whether it's single, double, or triple bonds. Around carbon, there are 3 electron domains. It is AB3 molecule. Now, you got to think which hybridization gives you 3 orbitals, because central atom already doesn't need anything. It's the host, right? So the hybridizations are when one S and one P combine together, it forms 2 orbitals, which are sp and sp. When 1 s and 2 hybridize together, they form sp2, sp2, and sp2, 3 of the sp2 orbitals. When s and 3 p's combine, they form sp3, 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 sp3. They form 4 sp3 hybrid orbitals. So you need 3 hybrid orbitals. So hybridization is sp2. And this is the extent to which you need to know that. Yes?
For sp2, why does it form an sp3 at the end?
That is because Mrs. Gupta is getting tired. That's why. All right. But it is sp2, all of them. And the bond angle here would be 1, 2, 3. Nothing changes. Bond angle will be 120 degrees. But now it can explain, this was hybrid orbital theory, it can explain molecule formation in terms of SPDF along with bond angles and so on. Yes?
Well, we have to know hybridization is the D.
No. So sp3d and sp3d2 exist. If there is a molecule which is actually sp3d2, but you only write sp3, I will accept it for full credit, as will College Board.
So the central atom doesn't hybridize, it's just the outer?
Central atom is the only one that hybridizes. So when I'm saying this S and P, these all are central atoms orbital. Side atom doesn't hybridize. So these are all of the orbitals of central atom. Do only S and 1 of the P of central atom hybridize, or do S and 2 of the P of central atom hybridize, or do S and all 3 P of central atom? So when I'm talking hybridization, I'm only talking about orbitals of the central atom. Yes.
Is hybridization independent of valence, like sigma and pi bond?
Totally.
Okay.
Totally. It goes with electron domains just like VSEPR does. So after all of this, what happened was, because VSEPR and hybridization all consider single, double, and triple bond the same, another theory was needed to explain why bond energy of single, double, and triple bonds are different, and why a double bond's energy is not exactly 2 times that of single bond. It is not. And that explanation came from valence bond theory, which said not all single bonds or double bonds and triple bonds are the same. Single bond is a sigma bond. In a double bond, first bond is sigma, but second is a pi. In a triple bond, first is sigma, second and third are pi. What is the difference? Sigma bonds are formed by end-to-end overlap. Whether you overlap that way, overlap this way, overlap a S and a P, or overlap 2 S's, all of these orbital overlaps are sigma bonds. Every first sigma bond, wherever you draw a single line, is a sigma bond. Every single line is a sigma bond. Because sigma bonds occur along internuclear axis, there's a lot of room for electron clouds to overlap. So sigma bonds are stronger than pi. Pi bonds can happen only between py or pz orbitals. This is one pi bond, this is another pi bond. Both top and bottom overlap, make one pi bond. This is not 2 pi bonds, this is 1 pi bond. Okay, pi bonds are double and triple bonds in any of the molecule. And one other thing you need to know here, guys, is if you have organic molecule like H3OH, let's say. What is the bond angle around carbon or hybridization? You count electron domains. 4 electron domain, no lone pairs. So hybridization will be sp3 bond angle 109.5 degrees, tetrahedral. If you look at hybridization around this oxygen, there are 2 lone pairs, 2 bonded. It's still sp3 hybridization. But now bond angle is 105, like water, because there are 2 lone pairs. It's almost like a AB2E2. So when they ask you for organic molecules, break it up in small chunks. Every of the central atom acts like independent things. So you're looking around that. Okay? Now, moving on from there, sigma pi. Now I am ready to move to bonding and types of solids. Do you have formal charge I didn't quite do? Do you have a need for formal charge? Anyone wants me to go over formal charge? Then one other thing I wanted to address is potential energy diagrams, which came with valence bond theory and bonding. And valence bond theory says, as the atoms approach each other to form a bond, the energy on the y-axis is energy. This is 0. This is negative. This is positive. So as the atoms attract each other, come closer, energy is released. And remember, release of energy is negative, and negative energy is shown with the negative axis here. And at the lowest energy point, we call it bonded state. So here, this will be the internuclear distance between these atoms when they are bonded. And then if they come too close, then the repulsion becomes greater than the attraction. And at this point, molecules will be completely separated. Okay, so this is a energy diagram showing overlap during a energy increases, and then the particles become apart. So this really is not bonded state. This is bonded state, right? In this, sometimes they give you questions like hydrogen versus chlorine versus bromine. What would it look like? You know, hydrogen being the smallest atoms, they will, according to Coulomb's law, will have most attraction with each other, right? So hydrogen's internuclear distance will be smallest, and its release of energy will be highest because of smallest radii. Chlorine's internuclear distance will be larger, but smaller energy. And bromine, this is chlorine, hydrogen. Bromine will be even larger with larger internuclear distance, but lesser energy because it's bigger molecule. Okay, do you guys have a need to explain anything further here? Yes.
Why do bigger molecules have a smaller release energy?
Coulomb's law. This is larger, so that is smaller. Okay, so I'm going to touch on MO theory again because I know a couple of you are still confused about it. So molecular orbital theory was yet put forth because according to all of the theories so far, oxygen should be diamagnetic, meaning it should show no magnetism when applied external magnetic field because it's got no unpaired electron. But scientists observed that oxygen is not diamagnetic, it's actually paramagnetic. So what is the reason why oxygen is paramagnetic? And the reason for that is explained by MO theory. MO theory says when atomic orbitals overlap. So this is atomic orbital of, let's say, hydrogen atom 1. And this is atomic orbital of hydrogen atom 2. And hydrogen atom has 1 electron in each. When they overlap, they form 2 molecular orbital. 1 molecular orbital is bonding MO, and it is sigma, and we call it 1s because this is 1s and this is 1s. And the higher energy one is called sigma anti-bonding 1s orbital. Electrons tend to occupy lower energy orbital first. So both of these electrons will go to the bonding orbital. And then if you had helium and added 2 more electrons, then they will go here. In case, and this diagram will be given to you. Remember, the diagram, filling diagram for elements up to nitrogen is different than oxygen and fluorine. You will be given these diagrams. You just need to be able to fill and calculate bond order. And unlike valence bond theory, where you could just eyeball or look at the number of bonds between 2 atoms, here you actually have to calculate. Bond order is equal to number of electrons in bonding orbitals minus number of electrons in anti-bonding orbitals divided by 2. And 3 things to remember here. If bond order is greater than 0, meaning positive something, then a bond forms. Otherwise, if it is 0, a bond does not form. A whole number is a better bond than a smaller fraction of it. So you can have bond order in fraction as well. Okay? And bond order tells you whether a bond forms, and it also tells you how many bonds are there. So for nitrogen, if you calculate, you know that there's a triple bond between 2 nitrogens, you'll get a bond order of 3. So bond order guides you into building the structure of a molecule. Yes?
If you have a fraction bond order, how would you draw that?
It is beyond the scope of our course. I'll be happy to do that. Okay, let's just stick with the majority of ideas here, but I'll be happy to work with you later on. Okay, now I got to move on to the types of bonding, otherwise the bell will ring. So now let's go over the types of bonds. And I'm going to address in this big giant table all inter and intramolecular bonds, okay? Because sometimes they are not different. So let's start ionic, then covalent, then metallic, then ion dipole, then hydrogen bond, then dipole, and then LDFs. Ionic bonds are formed by ionic compounds, and you identify them by presence of metal cation. When I say metal cation, I mean Mg2 plus, Al3 plus, not MgNaL, right? They are an ionic compound. So examples of these will be, can you think of any, guys? NaCl, MgSO4, K2CO3, right? All of these are ionic compounds. What determines the strength of ionic compounds? Who remembers? Lattice energy. And lattice energy comes from Coulomb's law. Force is proportional to product of charges and inversely proportional to the square of distance between them. Yes?
Is that what leads to electrostatic?
Yes. So the attraction is called electrostatic attraction, and the energy that's released when they come together is called lattice energy. Okay? Also, the charge kind of trumps the size because charge is more significant in determining, they are such small atoms, the atomic radius is only small difference.
Should we mention lattice energy, or can we just go straight to Coulomb's law?
Lattice energy. Yeah. Okay. Then here, some of the properties that you need to know. So before that, what are the attractions? So IMFs, inter and intra, are the same, right? And they are ion-ion or ion-ion or ionic bonds. And why they result is because of electrostatic attraction. But you must specify them as ion-ion attraction or ionic attraction. Now, some of their properties. First of all, let's take K2CO3. In solid state, if you had to draw K2CO3, then you will draw 2K plus and 1 CO3. The ratio is important. Okay, and in solid state, they are pretty close to each other, almost joined, K plus CO3, 2 minus. So you want to draw them closer. If it is K2CO3 liquid, then they will be farther apart. K2CO3, I did not draw them right. K2CO3, K2CO3, there should be another K here, K2CO3. And another K here, right? In liquid form, oh goodness, CO3, 2 minus, I'll continue, you can leave, and then you can watch the video, I'll just go on. So never mind me, don't leave without sound, you're welcome. K plus, CO3, 2 minus, they are farther apart. And if it is K2CO3 aqueous, then K plus and CO3 2 minus being farther apart also have water molecules around them. So when there are water molecules around them, there is attraction between them, and you know this attraction is ion dipole. And ion dipole attraction strength is also calculated by Coulomb's law, which is force of attraction is proportional to the product of their charges, inversely proportional to the square of their distance. Now, in solid form, ionic compounds do not conduct electricity because ions cannot move. And then if ions cannot move, then the electrons cannot sit on them and move and carry charge. So in solid state, the ionic compounds are non-conductors. In liquid state, they are conductors because now the ions are separated and they can carry charge with them. In aqueous state, they are conductors because now they are separated and can carry charge with them. In solid state, ionic compounds have pretty high melting point and pretty high boiling points because of strong ion-ion attraction. These melting and boiling points are only lower than that of covalent bonds when they are broken. Okay, so those are some of the properties of ionic compounds. Now I am going to erase it and move it to covalently bonded molecules. In covalently bonded molecules, you have all non-metals. You don't have any metals in there. CO2, CO, PCl5, SO3, all of these are covalently bonded compounds. They could be either non-polar covalent or they could be polar covalent. In non-polar covalent, you have the two atoms sharing electrons, so they are shared evenly, or the electronegativity difference is less than 0.3. That's when it is a non-polar bond. In a polar bond, your electronegativity difference is between 0.3 and 1.7. So they are still sharing a pair of electrons, but that is not evenly shared. As a result, a dipole is generated where Cl minus end of the molecule acquires a negative charge and here H plus acquires a positive charge. We call such molecules as dipoles. And generally, covalently bonded molecules like CO2 and H2O, they interact with each other either through LDFs if they are nonpolar. If they are polar, like HCl, then they interact with each other through what is called dipole-dipole attraction. So for a dipole-dipole, it must be a polar covalent bond. Okay. And typically, covalent compounds have low boiling point, low melting points. They are non-conductors, and all of these can be explained through their structure. They have low boiling and melting points because often you're breaking the intermolecular bonds. You're not breaking the covalent bond, right? While you're melting hydrogen or boiling hydrogen, you're not breaking this bond. You're breaking the LDFs between two hydrogen molecules. They are non-conductors because they generally don't have charge like nonpolar covalent. Okay, moving on to one more here, which is covalent network. And in covalent network, it's like a network of molecules or atoms that are joined to each other with covalent bonds. So SiO4 is one such molecule where every single bond is a covalent bond. Covalent network compounds you got to memorize. They are germanium, silicon, silica, carbon as graphite, carbon as diamond. These covalent network compounds are highly inactive because they're very stable. They're insoluble both in polar and non-polar solvent. And they have very high melting and boiling points. They are one of the hardest substances. So that is covalent network compound. Now moving on to metallic compounds. And metallic compounds are pure metal, aluminum foil, iron nails. All of these by themselves are just metallic. Metallic compounds have metallic bond, which is based on electron C model, where you have metal cations like Al3+, Al3+, which has lost its 3 electrons in the common matrix. And these 3 electrons are constantly moving, and wherever they are, they feel attraction from those atoms at that point of time. And this special model gives metals special properties of malleability, ductility, and metals generally have low melting points. You know, they melt fast. And malleable because of these delocalized electrons. As you stretch on a metal, it doesn't break, but those displaced metal atom cations will always find some delocalized electrons to attract it. Same thing with ductility. And the low melting point is because these bonds are there. However, because of delocalization, their bonds, metallic bonds, not very strong. Moving on to ion dipole, most of the aqueous solutions of ionic compounds show this type of bond. Hydrogen bond is a special type of intermolecular bond which is formed when a polar covalent bond is formed between hydrogen and N, O, or F, then the intermolecular bond is called as hydrogen bond. Okay, so if you have HF, now this is a polar covalent bond, right? And if there's another HF, then this attraction between negatively charged hydrogen, polarized fluorine and hydrogen, this is hydrogen bond. Note one thing, for hydrogen bond, you do not need HF on the other side. There is already enough polarization in this molecule, and if there is an electron, like here for hydrogen, there is fluorine. If there's another electronegative atom here instead of fluorine, it will still be hydrogen bond. Dipole-dipole attractions I just talked about. So hydrogen bond almost like is an extreme case of dipole-dipole attraction. London dispersion forces, or LDFs, are the last type of intermolecular bonds. And LDFs are present in all substances, every single substance, because they all have electron cloud. However, LDFs only become significant when they are the only force present, or sometimes in some alcohols where you have long carbon chain. Let me give you an example. So LDFs are the only IMFs in non-polar molecules because they don't have polarity, or in noble gases. So non-polar molecule will be like a hydrogen and another hydrogen, right? Between them will be LDFs, or N2 or Cl2. All of these will be LDFs. And in this case, the higher the molar mass, more the electrons, greater the electron cloud distortion, higher the melting point or boiling point. And that's the reasoning that goes on with that. It is the same reasoning for noble gases, for helium to neon to radon. Radon will have highest melting point or boiling point, and this one will have lowest, because the highest number of electrons here in radon will cause more distortion, more polarization. And remember, guys, LDFs are temporary dipoles. Polarization happens, then electrons redistribute, it disappears. LDFs generally are only significant when these are the only forces that exist, but LDFs also become significant when you have long carbon chain, like C, 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 C. So I'm going to give you two different scenarios here. In the first scenario, we have different size carbon chain, CH4, right? HH. Remember, every carbon needs 4, so you keep drawing H, 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 H. This one will have the highest boiling point because this is the longest carbon chain, most molar mass, highest distortion, right? This one will have lowest boiling point. Now, guys, let's replace the hydrogen with OH. Now, you know that molecule in between each of this molecule and another of its kind, this molecule, another of this kind, this molecule, another of this kind, there'll be hydrogen bonds, right? Each of these will form hydrogen bonds. That's a constant. But what else will happen in addition to hydrogen bond? This long carbon chain and straight carbon chain, because it has so much surface area, will have significant LDFs. And that results in a higher boiling point of this alcohol as compared to this. However, if you were talking about solubility of these alcohols in water, this one will have highest solubility in water. Because this is the smallest molecule. Remember, water is like this, right? It's a small molecule. For something to be soluble in this, they have to be able to arrange themselves around it, right? To attract the charges. If it's a smaller molecule, they can arrange better versus if it is a larger molecule, then they will have to rotate and come to that specific orientation. That is why the smallest of these molecules will have highest solubility. So please read the questions carefully. Are they asking about water solubility or are they asking about melting point and boiling points? Okay, is there any question I can answer for you guys?
Do we ever go over semiconductors?
No, not in this unit. We'll do later. But alloys, yes. And alloys are pretty simple, so I'm not going to spend time doing that. Remember, the larger the surface area, the greater the distortion. So the last thing here is straight chain versus if you have a straight chain 5-carbon compound versus 3 and 2 and 2, this is more surface area. Because it is more surface area, there'll be greater polarization and higher LDFs and higher melting and boiling points as compared to a more compact molecule. Okay, so I have Alan, it is not there. So, Stephen, that is not to say 2.5 is more likely than 2, but what you can say is 2.5 likely shows resonance and 2 does not show resonance. Also remember the pi bonds cannot be rotated. They're not flexible. So double, triple bond are rigid. Molecules cannot rotate around them or atoms cannot rotate, but single bonds are flexible and they can be rotated. So in CH3OH, the negative side really is this oxygen atom, and this is positive. So really the negative charge is here on oxygen. Anything else? All right, everybody, thank you for listening.